Page 17 of probability. Number 7. 400 families were surveyed. It was found that 90% had a TV set and 60% had a computer. Every family had at least one of these items. One of the families was randomly selected and is found that it has a computer. Find the probability that it also has a TV set. So this is kind of like, oh, what's the probability that they have a TV set given that they have a computer? Okay, so let's see. This would be equal to the probability that they have a TV set and a computer divided by the probability that they have a computer. This is just the formula that was given to us on the last page. Looks like we have the probability that they have a computer. It's right here. Now the question is, can we figure out the probability that a family has a TV set and a computer? Because they don't give us that. What they do give us is that 400 families total, and that 90% have a TV set and 60% have a computer. So how about if we figure that out? So the probability that someone has a TV set is 90% of 400 divided by 400. Basically, the probability that you have a TV set is 0.9, right? Probability that your computer is 60% of 400 divided by 400, 0.6. Okay. It also gives us a very important clue that every family has at least one of the items. So let's say we're going to draw a Venn diagram. If we drew a Venn diagram, we would see that we would have two circles. We'd have T and C. And the T circle is going to be 0.9. And the C circle is going to be 0.6. 0.9 and 0.6. But one important clue is that every family has at least one of the two, so we know that the probability of being outside of the two circles is 0. So that kind of helps us determine the overlap, right? Because we know now that the probability of T union C is equal to the probability of T plus the probability of C minus the probability of T intersects C. And we already know that the probability of T union C, they already said, is 100% or 1. So we know that's 1 equals 0.9 plus 0.6 minus the probability that T intersects C, which is, we don't know, X. Okay? So what's this going to give us? If we do the algebra on this, we're going to get X equals 0.9 plus 0.6, which is 1.5, minus 1, which is 0.5. So we have just found out that the intersection of these two, this fish area here, is 0.5. So the probability here on the numerator is 0.5. For the denominator, the probability of C is 0.6 because it's probability of having a computer. So the answer is 5/6. Okay, so basically we used two important formulas. We used the conditional probability formula, which is that the probability of the two events intersected is divided by the probability of the event that has already been has been given. And then we use the addition formula here, which is that the union of the two events is equal to the probability of the two events separate minus the intersection. Okay, so using those two, we were able to figure that out. Okay, what about number 9? Urn A contains 2 red and 3 blue marbles, and urn B contains 4 red and 1 blue marble. Peter selects an urn by tossing a coin and then takes a marble from that urn. Okay, so first thing Peter does is he tosses a coin. So he gets heads or tails, or maybe we should say A or B. Urn A, urn B. And what's the probability that it gets A or B? Well, since he's tossing a coin and the coin is fair, let's say that it's 0.5 probability of getting either A or B. If he gets A, then it's 2 red or 3 blue marbles. So What's the probability that he gets red? What's the probability that he gets blue? 2 red divided by 5 marbles total. 3 blue divided by 5 marbles total. Urn B contains 4 red and 1 blue marble. 4 red divided by 5 total to get red. 1 blue divided by 5 total to get blue. Okay. Determine the probability that the marble taken from an urn is red. So let's multiply out all these probabilities. So 0.5 times 2/5. By the way, 2/5 is 0.4. So 0.4 times 0.5 is 0.2. That would be for the event AR. So the event AR would be 0.2. And then 0.5 times 3/5 for the event AB would be, let's see, 0.6 times 0.5, which is 0.3. What about BR? BR would be 0.8 times 0.5, which would be 0.4. And BB would be 0.2 times 0.5, which is 0.1. And if you check, all these added together, 0.4 plus 0.1 plus 0.3 plus 0.2, give you 1.0, which is the way it should be. Okay, so let's determine the probability that the marble chosen is red. So that would be this and this. So it would be 0.2 plus 0.4, which is 0.6. We can just add those together because they're mutually exclusive events. Given that the marble is red, what is the probability that it came from B? Okay, so this is a what do you call it? A dependent conditional probability. Sorry. Given that the probability that the marble is red, what is the probability that it came from B? So what is the probability that it's urn B, given that the marble is red? And just to not get mixed up with blue, we're going to say, we'll say urn B. Urn B, given that the marble is red. Okay, so the way we figure that out is, it would be the probability of urn B intersect red divided by the probability of red. So the probability of urn B intersect red, where would that be? Urn B intersect red. That would be this one here, which is 0.4. What is the probability of just red? Well, we just figured that out in the first part, 0.6. So the answer is 2/3. Okay? Alright, number 11. On a given day, machine A has a 10% chance of malfunctioning and machine B has a 7% chance of malfunctioning. Given that at least one of the machines malfunctioned today, what is the chance that machine B malfunctioned? Okay, so the probability that A malfunctions is 0.1. The probability that B malfunctions is 0.07. Given that at least one of the machines malfunctioned, what is the chance that B malfunctioned? Let's draw this as a tree diagram. So the first event would be probability of A breaking and not breaking. Sometimes when you do the not, you put a line above the event. And then the second step would be B breaking or B not breaking. Oops. Okay. So the probability that A breaking, remember, is 0.1, which means the probability of A not breaking is just the complement, which is 0.9. 1 minus 0.1. Probability of B breaking is 0.07, so that means that the probability of B not breaking is just 0.93. We can repeat that here. Okay. And then we can multiply them together to get the compound events. So the probability of A breaking and B breaking would be 0.1 times 0.07, which would be 0.007. The probability of B not breaking and A breaking would be 0.1 times 0.93, which would be 0.093. And then the probability of A not breaking and B breaking would be 0.9 times 0.7, which would be equal to 0.63. And then the probability of, I'm sorry, that wouldn't be 0.63. It would be this would be 0.07, so it would be 0.063. Okay. And the last one would be not A breaking, not B breaking, which would be 0.9 times 0.93, which would be equal to, let me use the offline calculator, 0.9 times 0.93 would be 0.837. Okay. And the first thing they say is, what is the probability that B malfunction, given that at least one of the manufacturers of the machines malfunction? I'm going to represent with a 1. Okay. So basically, what they want to know, what is the probability of B intersect 1, given that the probability of 1. So what does probability of 1 mean? It means that at least one of the machines broke. So that would include this, it would include this, and include this, because those are all possibilities in which, I'm sorry. It would include this, and this, and this, because these are all possibilities, are all outcomes where at least one machine broke. I keep forgetting that, like, when there's no line, that means it breaks. Okay. So I'm going to add those three up, and then I'm going to get the probability equals 1. The probability of at least one breaking. So it would be 0.007 plus 0.093 plus 0.063. So the probability of at least one breaking is 0.163. That's the denominator. The numerator would be the probability that B breaks and that 1 breaks. So that would be B breaks. So it would be these two, right? It wouldn't be the not B one. So it would be 0.007 and 0.063. 0.07. So the top would be 0.07. The bottom is 0.163. So let's divide that out. And we get 0.429. Okay, so that's the probability that B is the one that malfunctioned if at least one malfunctioned. Okay. 13, which is the last one. The probability that a randomly selected person has cancer is 0.02. The probability that he or she reacts positively to a test which detects cancer is 0.95 if he or she has cancer, and 0.03 if he or she does not. Determine the probability that a randomly tested person reacts positively, has cancer, given that he or she reacts positively. Okay, let's draw a tree diagram first. Probability that a randomly selected person has cancer is 0.02. So we'll say has cancer, does not have cancer. Has cancer, there's a 0.02 probability, and a not cancer would be 0.98 probability. Okay. Probability that he or she reacts positively to a test which detects cancer, I'll note that as T, is 0.95 if he or she has cancer, and 0.03 if she does not have cancer. So, like, even if you don't have cancer, some of these cancer tests might detect that you have cancer mistakenly, and that's a 3% chance. Then, of course, the not T possibility is just the complement of each of these. So this would be 0.05, and this would be 0.97. Okay. Determine the probability that a randomly tested person reacts positively. So that would be which outcomes? It would be the outcome CT, and it would be the outcome C naught T. Right? Those are two outcomes in which it reacts positively. So to find these probabilities, all we need to do is multiply the probabilities in cascade. So 0.02 times 0.95 is equal to 0.019. And then C naught times T is 0.98 times 0.03, which is 0.0294. And so adding these two together is going to give you the answer to reacts positively. I know we're going to need more than this, so we're going to go ahead and multiply everything out. So we'll do CT naught and C naught T naught. C naught T naught is 0.98 times 0.97, which is 0.9506. And the top one is 0.02 times 0.05, which is 0.001. Okay? So first of all, we're going to calculate reacts positively. So we're going to add up 0.0294, and we're going to add that to 0.019, and it's going to be 0.0484. 0.0484. And then B, has cancer given that he or she reacts positively. Has cancer given that he or she reacts positively. So has cancer would be C. It would be the C option. Has cancer given that she reacts positively. So that would be the probability that she has cancer given that she reacts positively. So that would be equal to the probability that C intersects T divided by the probability of T. So the probability of C intersect T is this one here, which is 0.019, right? C intersect T would be both C and T happening. The probability of T we would find by adding up, we already found that. The probability of T is, we found that in part A, it's 0.0484, right? So now we just divide 0.019 divided by 0.0484, and we get 0.393. And that is the answer. Okay. Last of all, independent events. A and B are independent events if the occurrence of each one of them does not affect the probability that the other occurs. So, knowing that B occurs, what is the probability of A? Knowing that B doesn't occur, what's the probability of A? Basically what you're saying is the probability of A is equal regardless of whether B happens. So the conditional probability of A happening given B and A happening given B not B is going to be the same thing as the probability of A. Okay. And that's what we're going to do in page 18 on a separate video.